First of all, I would like to thank organizing committee for their kind invitation. It's a great pleasure for me to be here and to discuss our recent results with you. As the title of my talk states, I will talk about the coherent coupling between the interlayer excitons, between the two different spin states of the interlayer excitons in TMDC heterobilayers. This is the cover art we recently published, as you can see. This shows the interaction between two different spin states of the interlayer excitons. After Professor Finley's talk, I will pass my intro part quickly because he gave a very nice introduction about the interlayer exciton photophysics. Yeah, why interlayer excitons are important? Because they have very exceptional properties compared to the intralayer ones. For example, they have long photoluminescence lifetimes up to microseconds. Also, because of electron and hole separated in different layers, they have permanent out-of-plane electric dipole moment. It means that you can tune the emission wavelength by using the external electric field. Using those exceptional properties, different optoelectronic and quantum photonic devices have been developed in recent years, like transistor, mid-IR detector, interlayer exciton-based lasing, also quantum light sources. In order to use interlayer excitons in valleytronic devices efficiently, one has to also know in detail the fine structure of the interlayer excitons. And very recent theoretical work showed that in addition to spin singlet interlayer exciton, the triplet interlayer exciton is also bright because of the breaking of the out-of-plane mirror symmetry in the heterobilayer. In the monolayer, it is dark because of the out-of-plane mirror symmetry. Then, it is also experimentally confirmed that both singlet and triplet emission can be observed from the, let's say, tungsten diselenide, molybdenum diselenide heterobilayer. At this point, we ask the question, is there any interaction between those two different spin states? If there is, what is the nature of this interaction? This is our question, and at the end of my talk, I will answer this question. Here, once we have heterobilayer, let's say HBN encapsulated tungsten diselenide, molybdenum diselenide, we are loading the sample into the Attodry 1000, and we can do all of those cool experiments using the micro-PL setup in our lab. We are using two different lasers during those studies. One of them, 532 nanometer laser for the off-resonant excitation. The other one is the 730 nanometer laser for the resonant excitation in the intralayer exciton emission of the tungsten diselenide. Here, this is the optic microscope image of the heterobilayer. Because of the conduction band splitting of the MOSE2, as you can see, two spin states of the interlayer excitons can be formed. One of them is singlet, the other one is the triplet interlayer exciton. Here, this is the low temperature photoluminescence spectrum of the WSE2 MOSE2 heterobilayer. As you can see, in addition to suppressed intralayer exciton emission, we have low energy interlayer exciton emission with the two different spin states. And the energy separation between those two spin states is around 24 MeV, which is the conduction band splitting of the MOSE2. In order to confirm the assignment of spin singlet and spin triplet interlayer exciton emission, what we did, we performed magneto-PL studies with these two emissions. As you can see, at the beginning, once you have no magnetic field, this single peak evolves into two. Then you can calculate the energy separation between those two peaks, and you can get the corresponding lambda G factors. And for the spin triplet, it is around 15.4. For the spin singlet, it is around 12. It means that it confirms that the stacking angle between WSE2 and the MOSE2 is around 60 degrees, which means that we have AB stacking or H-type stacking. Then, in order to study the coherence properties of both spin singlet and spin triplet interlayer excitons, what we did, we construct the simple Michelson interferometer. It consists of the 50-50 beam splitter and two retro mirrors. Changing the path length of the arm of the interferometer, you can get bright and dark fringes at the output of the beam splitter. Here, first, we study the coherence properties of individual peaks. First, we spectrally isolated the singlet peak. Then we sent this emission to the interferometer. As you can see, this is the PL interferogram we obtained by using the Michelson interferometer. As you can see, we got very nice high contrast fringe pattern near zero delay time. And same, by using the bandpass filter, you can also spectrally choose the triplet interlayer exciton, and you can get the corresponding dephasing time as well. As you can see, we plot the visibility versus visibility values in the semilog plot. And as you can see, around in the first 150 femtosecond time scale, there is a kick here, and it means that the fit deviates from the exponential fit. Because of that reason, we use Gaussian fit. It means that our line width is inhomogeneously broadened. And we also calculate corresponding homogeneous line width by using the T2 values. It is given by 4.7 MeV for the triplet one. It is around 5.1 for the spin singlet one. When we are calculating those values, we also consider the contribution of the T1 as well, but the contribution of the T1, the spontaneous emission lifetime, is rather small because of the time scale. And as you can see, once we look at the PL spectrum in the time-integrated PL spectrum, once we look at it, as you can see, our spectrum is inhomogeneously broadened. Then, finally, we studied the interaction between those two spin states by using the quantum beat spectroscopy. Once you send two energetically close emissions to the interferometer, you will observe interference phenomena, which is called beating or periodic oscillations. Okay, but according to the depending on the interaction of the two states, whether they are coupled or uncoupled, the microscopic mechanism will change. For example, if you have two uncoupled two-level system, when you send these two emissions to the interferometer, you will still get beat pattern. But in this case, it is because of the interfering of the polarizations of independent quantum mechanical system. In the second type of system, once you have two states with the common ground state here, when you send those two emissions to the interferometer, you will get so-called quantum beat. It is because of the quantum mechanical interference due to the coupling of the transitions via the common ground state. Here, this is our case. As you can see, singlet and triplet interlayer excitons takes their hole from the same valence band of the tungsten diselenide. It means that they have shared ground state. So once we send those two emissions together to the interferometer, as you can see, we get very nice quantum beat pattern. And once we fit this beat pattern, we have beat dephasing time, which is around 300 femtoseconds. By using this value of the dephasing time, one can calculate the corresponding line width, which is around 9.4 MeV. It means that we also calculated, I showed you in the previous slides, we also calculated the line widths of the individual peaks. As you can see, the summation of those two nearly equal to the line width of the coupled state. It means that those two states coherently coupled to each other. And from this result, we can also say that spectral fluctuations giving rise to the inhomogeneous broadening in each line width are uncorrelated. Because of that reason, we are observing very strong damping of the quantum beats within the 300 femtosecond time scale. We can also extract the quantum beat period from the interferogram, as you can see, by taking the difference between two fringe maxima or minima, okay? When you take this value, it is around 200 femtosecond. The corresponding energy separation between the spin singlet and spin triplet corresponds to 21 MeV. And this is very well in agreement with the energy separation which we get directly from the time-integrated PL spectra. As you can see, it is around 23 MeV, which is close agreement between there is a close agreement between the calculated and experimental values. It again confirms that there is coherent interaction between those two states. In order to understand the dephasing mechanism behind the quantum beat pattern, we also performed pump power dependent quantum beat measurements by using two different excitations. One is off-resonant 532 nanometer laser. The other one is on-resonant 730 nanometer laser. As you can see, we can see very nice quantum beat pattern up to 5 fringes. And the T2 values change between 270 to 400 femtosecond. Once we change our excitation wavelength to the on-resonant excitation 730 nanometer, we see still similar dephasing time values compared to the off-resonant one. Why we are seeing similar values? If you look at 100 microwatt data, as you can see, the data from the 532 nanometer laser here for the 400 microwatt, whenever the intensity of those two peaks are comparable, we are getting the similar T2 times. So we can say that similar numbers of interlayer excitons might have been created via two different mechanisms. In the case of 532 nanometer, we are doing strong pumping, whereas in the case of 730 nanometer, with resonance with the interlayer exciton of tungsten diselenide, we are doing resonant enhancement of the interlayer exons, okay? Because of that reason, it is giving rise to similar T2 times caused by the exton-exton scattering. How much time I have? Okay, I will conclude. Okay, in the next step, we also perform temperature-dependent quantum beat measurements. As you can see, again, by using the two different laser excitation, once we, at the low temperature, 3.5 Kelvin, as you can see, spin triplet interlayer exon emission dominates the spectrum because in H-type stacking, optically active ground state is the triplet one. Once we increase the temperature, as you can see, the intensity of the spin singlet increases while the intensity of the triplet one decreases. At 90 Kelvin, we have nearly equal intensities. And these are the corresponding interferograms for 532 nanometer excitation. We performed the same experiment with the 730 nanometer excitation, and those are the corresponding interferograms. We have nearly same T2 times under both excitation. We can conclude that two different mechanisms can contribute to the dephasing of the quantum beats. One is interlayer exon acoustic phonon, low energy acoustic phonon interaction below 150 K. The work published in 2020. Another work says that the excitation-induced dephasing is inversely proportional to the square root of the temperature. By considering those two ideas, we can say that at 90 K, the main cause of the rapid decay of coherent coupling is the interaction of the interlayer exons with the low energy acoustic phonons, whereas at 3.5 K, it is mainly created by the interlayer exon interactions, and it is dominated or determined by the dephasing time of the triplet interlayer exon itself, because it dominates the spectrum. With that, I think this is my last slide. There is a summary slide. In this work, we show for the first time coherent coupling between spin singlet and spin triplet interlayer exon, and we measure as a signature of the coherent coupling quantum beats with dephasing time of reaching up to 400 femtosecond. The calculated energy difference between spin singlet and spin triplet and the experimental value is nearly equal. It means that they are coupling coherently. This is the cover art we published very recently. With that, I would like to also thank my group members, especially Mehmet Atif Durmuş. He is also here. He did most of the work in this study. Also, our funding agency, TÜBİTAK, for supporting us to realize those kind of measurements. Thank you for your attention.